Okay, tilt this up a little bit. Or is it this way? Haha, I am obviously not the artsy type of person that's used to working with cameras. But we're recording now. So introduction, plate tectonics. So when is your homework due? Monday. So hopefully you have maybe done some of your homework. Okay? And if you have done some of your homework, then you should be able to tell me at least a little bit about what plate tectonics is. So what is plate tectonics? Excellent. So we got continents and oceanic plates that shift. And what are those plates? Where do we find those plates? Crust and upper mantle, but it's the top layer of Earth. So plate tectonics is a theory. It is a theory. We're going to review that concept in just a few moments. A theory that states that Earth's lithosphere, and we'll talk about what the lithosphere is part of this, is broken into plates that move due to heat from the mantle. So, we're going to break this apart a little bit one by one. We'll start with this theory. We talked about what a theory was in science we talked about either in the second day or third day of class, right? So it's been a while. It was part of that 0 unit that was that first week of class. So what is a theory in science, and how is it different from theory in everyday language?
Isn't it? It's been experimented a lot, but it hasn't been disproven yet.
Right, so how do scientists treat it?
As true.
As true. Excellent. So Caitlin and Catherine have it. A theory is an idea that has been tested many times, and scientists accept it as true. Doesn't mean that it's impossible to prove wrong, but it's extremely unlikely because it's been through thousands and thousands and thousands and thousands of different tests and different modes to show that it's true. Okay, and every single time it comes out and it shows that it's true. So plate tectonics, this idea that these moving plates change the way the surface of the Earth looks. And the great thing about plate tectonics, geology has one up on physics. There's always that kind of physics versus geology, like friendly rivalry there. This one we have up on the physics because we have a grand unifying theory, a grand unifying mechanism for most of the things that we see on Earth. And that grand unifying mechanism is plate tectonics. Now, what do we mean by grand unifying mechanism? It means it explains a lot of different things that we observe on the surface of the Earth that we couldn't explain before or without it. So some of the things that plate tectonics helps us explain include why we find sedimentary, igneous, and metamorphic rocks where we do. Why do we see metamorphic rocks up in A Bay? Where did those metamorphic rocks come from? Why do we see layers of sedimentary rock that were deposited in an ocean here in Watertown? How did that happen? And plate tectonics helps us explain that. Explains the distribution of earthquakes and volcanoes. Why some places get lots of earthquakes, like California, and why some places get almost no earthquakes, like the North Country. The origin of continents and ocean basins. The distribution of fossil plants and animals. And actually, this is what first implied that plate tectonics, or at least continental drift, we'll talk about the difference between the two of them, was an important idea, and that it was correct. Is this idea that we saw fossils in Africa and South America that were of land living animals, animals with little short stubby legs that walked around on land. Why would that be surprising today that we find those same animals in South America and Africa? Because they're really far apart. Excellent. Seth's got it. They're really far apart. They're separated by the Atlantic Ocean, and a critter with little stubby legs isn't going to dog paddle its way across the Atlantic Ocean. So why do we see those fossils where we do? And then finally, the creation and destruction of mountains and mountain chains. So before plate tectonics, scientists, geologists knew that something had to be pushing the rock upwards, but they had no mechanism for it. They had no idea what was actually causing that push. And now that we understand convergent plate boundaries and divergent plate boundaries, we have a better understanding of where that's coming from. So continental drift is an older idea. Plate tectonics is super duper new. Plate tectonics really got started in the 1970s, which is super recent, at least to me, because I was born in 1980. So this idea that that is the foundation of my field was not developed until about 10 years before I was born is mind-blowing to me. Continental drift is way older. Continental drift, we're talking about the 1910s, okay? And this is the idea that the continents move. Plate tectonics explains continental drift. So, and it wasn't because scientists were stupid, and it wasn't because, they weren't making, they weren't smart as us, and it actually doesn't take a huge amount of technology, but the important technology that brought us from continental drift, which wasn't hugely accepted at first, to plate tectonics, which was by the 1970s very well accepted, was actually World War II and the science of submarines. Because 3/4 of the Earth is under the ocean, and two of the major plate boundaries that we'll be talking about that play a role in the creation and the destruction of the lithosphere, convergent and divergent plate boundaries, are only viewable on the ocean bottom. So we didn't even know that they exist. We saw a lot of transform plate boundaries, but we couldn't make those observations on convergent and divergent plate boundaries until we could get down to the bottom of the ocean. Now, I know some of you may have learned the word crust. I want you to wipe the old Etch-a-Sketch, because calling plates made out of crust isn't quite completely correct. Tectonic plates are made out of what's called lithosphere. Lithosphere is the rigid upper layer of Earth. And it includes all the crust and the very top of the mantle. And like I mentioned in the opening, it is rigid, it's stiff. Whereas the asthenosphere is the mantle below the lithosphere, and it is much more what's called plastic. In other words, it's kind of soft and can be deformed. So, to think about this, you might see my silly putty up here at the front. Yes, here's my silly putty. Okay, so we've got my silly putty here. And we talked about this, we used silly putty back with glaciers too, right? And I can take my silly putty and I'm gonna go ahead really quick, make a bunny. There you go, here's a bunny. Not a good bunny, but it's good enough. So is silly putty a solid or a liquid?
It looks like a slug.
It looks like it looks like a slug. So it's a solid, right? Okay, because we can't take liquids and sculpt things out of them and have them hold that shape, right? So silly putty is a solid. However, as we saw with the glaciers, if I leave this silly putty here, what's going to eventually happen to that silly putty? Yeah, it's going to very, very slowly flow out and make a puddle. So, if I have my, I'll actually use my Geology of the State of New York. Okay, so I have a book, Geology of New York, and I have my silly putty. Which one do you think is more like the asthenosphere and which one's more like the lithosphere? Is the asthenosphere, why?
Because it's
Bendable.
Bendable, it's soft and it's malleable and it's more plastic. So the book represents the lithosphere. Okay, so we have the lithosphere on top of the asthenosphere. Now I don't want you to picture, it's not really the texture of silly putty, okay, any more than rock is really the texture of the book. Okay, these are just analogies. It's really much more rigid than that. But over long periods of time, the asthenosphere behaves much more plastically than the lithosphere does. It's much more like the silly putty than the lithosphere is. So lithosphere tends to bend elastically when loaded because it's more rigid like the book. And asthenosphere flows plastically when loaded. And when we say loaded, that's a very fancy, sciencey way of saying put a big weight on it. Put a massive weight on it. So here we have an example of a load, and can you think of things relative to the Earth, really massive things that might be loads on the lithosphere? Mountains, that's a good example. So some examples of loads might include mountains. What's another one?
Plateaus.
Plateaus, mountains, plateaus.
I think we talked about deltas too in GO 131.
In 131, yeah, deltas and a lot of sediment, but I don't want to.
Oh, sorry.
No. So mountains, massive piles of sediment. What's one big temporary load that we've talked about? We talked about it in Unit 2.
Glaciers.
Glaciers, excellent, Abigail. So glaciers. So when these kinds of loads are placed on the lithosphere, it causes the lithosphere to bend and the asthenosphere flows away. Just the same way as if I put my hand as this weight on this book with the silly putty, the book is bending, but the silly putty is flowing away from the pressure. Does that make sense? Awesome. Now this is important for understanding what's going on with plate tectonics, because we're not, it's not like a raft floating, when people say, oh, California is going to sink into the ocean. No, that's the wrong way to picture things, okay? You want to imagine a very relatively stiff, rigid thing on top of something that's kind of soft and can flow. So, I am going to go walk through this, and then we're going to step over to the other room and finish up the activity. So, in the opening of this, you'll be given graham cracker and frosting, and that's what the models are made out of. Why we're using graham cracker and frosting, it's cheap enough to make models out of, and then you can eat them. And in this part of the semester, a little relaxation and sugar is a good thing. So there's a couple of thinking questions, and then there's these diagrams of divergent, convergent, and transformed plate boundaries. Now, thinking back to earth science in high school, which way do plates move in a divergent plate boundary?
Away from each other.
Away from each other. Excellent. So they move outwards. What about in a convergent?
Towards.
Towards each other. Excellent. And what about transform?
Next
next to, so they slide past each other like this. Awesome. So that motion and the pressure and the forces of the plates can create different features. So for example, in a divergent plate boundary, the motion creates these mid-ocean ridges. In a convergent plate boundary, it forms these trenches and volcanic arcs. Now these are what's called block diagrams. They're 3D diagrams, and they can be pretty hard to sketch. So one of the things, I'm just going to show you a simpler way to sketch it from a side view, what's called a cross section. So in a divergent plate boundary, to draw a cross section, we're just going to draw this front face of the block diagram. It's saying exactly the same thing, but we're just taking that front face because it's a little easier to draw on a test. And we go like this. Now what are these parts called? What part of the earth are these? It's this layer in here. Lithosphere, that's the one on top. Excellent, Seth. What's the layer underneath that called? Asthenosphere. Excellent, Caitlin. And then where is my mid-ocean ridge in this diagram? Looking at this diagram and kind of trying to connect it back to this cross-section. Where they're touching, exactly. So right here is my mid-ocean ridge. Same too with the convergent. Okay, I'm just going to draw this front face down here and make it a little bit simpler of a diagram. So we have one plate here, and then we have another plate going underneath it. The plate that's going underneath it is, it's lithosphere, but it's what's called subducting. Whereas over here, this is lithosphere. And underneath is asthenosphere. And these are layers, so when you make these kinds of sketches, you want to make sure that it's really clear that this is a distinct layer. Now, where is the trench in this diagram? Looking at this diagram here, and keeping in mind the trench is a hole. And this,
like corner they're creating.
exactly, this right here, that's our trench. Now, as that lithosphere goes into the asthenosphere, what's it going to start to do? What's the temperature like down there? And it might melt, and it's going to heat up. And with the water, it's going to start melting. So if it melts, and that melting material rises, that will form a volcano. So for example, in this diagram, the volcanoes are called volcanic arcs because they're on a continent. If they were in an ocean, they would be called oceanic arcs. So I want you to think back to these diagrams. Always think back to the real features in the real world, like trenches, volcanic arcs, mid-ocean ridges. If I ask, what does this represent? Think about, like, what feature are you making there? And so you do 1 through 4. Number 4 is a check. You'll be able to eat your lithosphere at that point. Raise your hand for more lithosphere and asthenosphere. And then you'll work through the next 4 at number 8, and that is also a check. Make sense? Excellent. Let's go over to the other room. I will get you guys, turn off the camera, go over with you guys, distribute the grids, and then grab the camera.
Can I do the activity with you on another day?
Sure, yeah.
I just wanted to stay for the notes. So
No problem, no problem. And it'll be in the video, which I'm not editing them, so this particular video is going to be hilarious because we have my big fat face in it.